So let's, I'm gonna sort of close out before I get on to the, close out the pre-module section with a theorem that will probably look sort of familiar, maybe back from the old, linear algebra / vector spaces day. And here I'm talking about a vector space over a division ring. So let's let W in V the subspace of vector space over D, where D is a division ring. Number A. The dimension, and here by dimension, of course, I mean the cardinality of the basis set is less than or equal to the dimension, the cardinality of the basis set of V. Subspace means it's got less than or equal to basis elements. Here's a follow-up to this. If the dimension of W is equal to the dimension of D, or I'm sorry, the dimension of D, and if this is a finite dimensional vector space, then W equals V. This follows from what we did last time, because notice that W has the same dimension as V. So take a basis of W, right? That is a maximal linearly independent subset of W and of V because their dimensions are the same, right? So since their dimensions are the same, W is also a maximal linearly independent set, and so they actually this is a base P. Notice that this is not the same if you have an infinite dimensional vector space. It's possible for the cardinalities to be the same, but they not to be equal. Right? So C. This is, I mean, one might construe this as the part isomorphism theorem in disguise, sort of put in our situation. If F from V to W is a linear transformation, then we have that the dimension of the kernel of F plus min. Right. By the way, this one doesn't really require that W is a subspace of V. And E, yeah, we need to say it. If V and W are finite dimensional, then the dimension of V plus the dimension of W V plus the dimension of W equals dimension V intersect W what's the dimension? Let me point out, again, these last two don't really need the W subspace. Let me point out in this last one, you can consider V plus W as a vector space that contains both V and W, right? I mean, certainly everything in V is in V plus W and everything in W is in V plus W. What happens if this intersection is as small as possible? Right, the intersection being small as possible means the intersection is 0. Agreed? And if this intersection is 0, that means the sum is a direct sum, right? And so the dimension of these two components is the dimension of the whole direct sum. Okay, any questions on that? Okay. So now I want to talk about projective and injective models. It turns out that projectives, these are nice properties that a module might have. Now, let me point out that if you have a module over a vector, or I'm sorry, over a division ring, right? If you have a module over a division ring, it is always a vector space, and therefore is always free, right? So any vector space V is a direct sum of a certain number of copies of the division ring, right? So, for example, any vector space over the real numbers is a direct sum of a certain number of copies of R, right? So, for example, this is kind of a fun example. Any 1 to infinity. Oh, by the way, this is kind of a good Zorn's lemma. Let me start this example. Simple. Well, that's a fun one. I mean, this is basically the content of linear algebra, right? I mean, don't tell the 31 didn't people that, but this is, you know, you spend all this time studying Rn and you study linear transformations and such. Here's another vector space over R. This is a good, this is sort of the analog of Rn at the infinite level, if you will. These are all sequences of real numbers, but it's a direct sum, so it has to end in an infinite string of zeros. Do I agree with that? And of course, I can just extend the basis, the natural basis of this is E1, E2, all the way up to En. I can just extend that forever and make a basis of this. Do I agree with that? Now, let B equal the direct product of R. And this is so now it's countable sequences, but now I have no restriction that I can end an infinite string of zeros. Is E1, E2, E3 forever a basis of this? No, because you cannot write everything in there as a finite linear combination. It is, however, a linearly independent subset, right? You can expand this to a basis. If you all are getting sick of this class, write that basis down for me. Take E1 up to infinity and expand it to a basis. show it to me and prove that it works, and you can leave. I'll just give you an A in class. You can spend the rest of your semester at the turf if you like. Good luck. Right. Requires the action of choice. In fact, here's the interesting thing. V is actually the direct sum of R. But the index set is big, lambda n big. The index set is more than countable, so it's actually bigger than this right here. Right. The direct product can be redone as a direct sum over a bigger index set because every vector space over real is a direct sum of the number of copies of R. We proved that every free module is that way. It's just that index set that I'm taking the direct product over is not big enough in this case. Kind of weird, right? But at the end of the day, this sort of makes free modules easy. It makes modules over fields easy. So one can say that all the stuff that you learn in linear algebra basically just comes from this business about the direct every vector space is direct sum of some number of copies. And so all the modules over a vector space, they're just sums of that. Now, in general, there are Z modules that are certainly not direct sums of numbers of copies of Z that are not free, right? Q is one of them. You cannot write Q as a direct sum of some number of copies of Z. Z mod 6, no chance there, because Z mod 6 has got 6 elements, and the direct sum of some number of copies of Z either has 0 elements or it has infinitely many, right? So there's lots of things that are not free. Here are two important types of modules that are not necessarily free modules. So let's get into the definitions. And I'm going to carry on these definitions sort of in parallel because I want you to see that these are kind of dual notions. Definition, first of the projectives. Consider the following diagram of R modules with the bottom row exact. R modules with bottom row exact. So we'll say A and I'm going to call this G, and I'm going to use P. We say that P is projective if there exists an R module homomorphism H from P to A such that when you do H and G, it's the same thing as doing F. So if you have an R module homomorphism that's onto and some random, we say P is projective, if given any random R module homomorphism, there's a homomorphism from P that goes on to sort of the bigger one that makes a diagram for you. So in other words, this F lifts to what ostensibly is kind of a bigger module, right? Because this is onto. Right? That's what it means to be projective, because given this, I can project P onto A. Right? There is a dual notion, which I've defined in your homework, but I will of course here as well. Definition 662. Consider the following R module diagram of R modules. R modules with an exact top. Let's see. Yeah, I'm going to use G again, unfortunately. 0, A, T, G, and F. We say that I is injective if there's an R module homomorphism there exists H when B to I. I'm sorry, it's going to be the other way. Yeah. If there is an H from B to I, right, such that when I do G and then I do H, it's F. Right. So in this case, so notice that this is kind of the mirror image of what happened here, right? Given this onto and a map from P to B, I can lift this to the bigger one, right? Now what happens is I have a homomorphism in the other direction from A into this injective object, right? And A is 1-to-1 here. So in other words, A in a certain sense is a submodule of B. So what this means is given a function or a homomorphism that is from little guy onto I can lift that to a homomorphism from big guy onto I. Injective objects for like most of the walk-a-day life, in a certain sense, with the kind of math I do, projectives are more important usually. That's not to say that injectives are not important, but it's sort of harder over standard rings you look at. It's sort of harder to find something that's injective than it is to find something that's projective, right? And we'll look at some examples of this. In a certain sense, injective objects have to be very, very big, right? Okay, so let's start taking this apart. And this is actually, in a certain sense, for the kind of stuff that I do, this is one of the things that sort of makes projectives sort of more important to me. So here's the first theorem. Every R module, every real is proof. Okay, by the way, notice I have not given you any examples yet because I want to develop a little bit before I actually give you some interesting examples of this. However, already this gives me a large family of sort of trivial examples, right? So if I want a projective module, all I got to do is just spit out a direct sum of the number of copies of the ring of a free module. That's going to be projective automatically, right? Although, as you might suspect, although this theorem is important, this is really kind of an unsatisfying collection of examples. So let's prove this. Let's see, what does it mean to be projective? So we have, so let's give them this diagram here, A into B into C, and this is onto. And let's say we've got a free that goes to here, right? I guess we call this F. Now, to show that F is projective, we need to somehow take this homomorphism and lift it to sort of a larger one, A. We need to find out how to get it. So what we're going to use is the basis, because the cool thing about free modules is basically when we looked at the equivalent properties of free modules, basically what that says is every homomorphism from a free module somewhere is determined by just a function on the basis. So all we have to do is be smart about where to send bases. So let me give you kind of an idea here. How am I gonna get from here to here that's gonna make the diagram commute? Well, just look at everything in the image down here, right? Everything here has a pullback here, right? And so just take your basis set and send it over to something appropriate here. Let's make that more concrete. So we'll say that F is free on X. I guess I should start here. So let F be free on X. So think of X as sort of the basis of that. And as per the theorem that we talked about pre-modules, this is going to be just kind of a canonical inclusion from the basis into F. So iota identifies with every element of the basis set, the appropriate element, the inclusion element, or the inclusion to that element in F. Since G is onto, then we can find an AI such that G, well, AI such that G of AI is equal to F iota Xi. Right. Remember, this is well, actually, I'll just write this clearly. What we're doing is we're taking every basis element here. It's actually an F, seeing where it goes here, right? Now this basis element has an AI, and it goes to F iota Xi. So for every basis element Xi, see where it goes here and see what it comes from, right? Because I can get away with this because this is onto. So this gives a function I'm going to call it F star here from X into A. Right. And by the way, well, let me point out, just so that we can take care here, my AI might not be unique, but for every XI basis element, we make that choice, right? So there's a choice going on here. Such that F star Xi equals AI. And that's that function here. So as F is free, we have actually I'm going to call it, so I should probably call it H. H from F to A. Right? Because this function F star from X to A induces H, which is now an R module homomorphism. That goes from H to A as promised. And what this R module homomorphism does is H iota of Xi is HI, or is AI. And so all we have to do now is verify if this makes the diagram commute. But notice that you look at G H iota xi, this is equal to G, well, notice HI iota xi is exactly GAI, which is the same thing as F iota xi. And hence, F. And so F. So just basically by specifying where every basis element goes, I'll lift it to the homomorphism. This probably isn't surprising because what this says is given this homomorphism here, and the fact this is onto, I can lift this to a free module. And free modules are uncommonly good because all you have to do is tell the basis element where to go and you're good to go. So this is probably not terribly surprising, but it will be useful moving forward. Let me give you a quick definition before I do something with injectives here. How many of you have ever heard of anybody ever heard of a divisible abelian group? This is. Okay, well, I'll show you. Definition. Six, 6, 4. Let D be an abelian group. We say that D is a divisible abelian group. We say D is divisible. Basically, if you can divide by any integer, whether you make that more precise, is divisible if for all D and D, there exists D prime D. For all D and D in natural numbers, there exists D prime in D, such that D is in D prime. So let me be a little bit sloppy here. So I like to think about this way. D prime is sort of D over N, and that's why. Well, my guess is that's why it's called divisible. But more formally, what that means is, what this means is given any integer, there's something that is, there's another element in there that when you add it to itself n times, it's equal to this, right? Can you give an example of a divisible abelian group? That's right. Actually, that's a pretty good, that's a very sort of compact, in a certain sense, that's kind of a small example, but you go bigger than that. You go the reals, the complex numbers, these are all divisible abelian groups. Okay, how about a divisible abelian group where every element has finite order?
C prime,
What's C prime?
like a Z mod prime, maybe.
Oh, right. But the problem is that you're gonna run into problems with primes, the prime itself, probably out there.
Q mod Z.
There you go. That's a good group. And that extends to Q to R mods and C mods. So, example, Q is divisible as is Q mod Z. Right. Notice in Q mod Z, every element has finite order, because take a typical coset in Q mod Z and just think of it as a rational number A over B. When you add that to itself B times, you get A, which is an integer, which is 0 in this ring, right? So every element has finite order, right? But it's certainly divisible because taking A over B, what would, given A over B and N, your D prime would be A over BN, right? So no problem. So these things exist, but they're very big in a certain sense. So here is kind of the point, and this lemma here actually gives you really, I'm not going to go too deeply into injectives, but if you're interested, you can come talk to me about it. But this kind of gives sort of the seeds of what's important about or where injectives come from. Lemma 665. It turns out that D is divisible if and only if D is an injective Z module. So this right here really characterizes what it means to be injective for R modules when R is Z, right? Proof. Exercise. And you'll have to do some thinking about this, I think. Here we're going to prove that if it's an injected Z module, then it's divisible. And let me start over here. So let's suppose that D is injective. As a Z module. And we want to show that it is divisible. So let's let D be in D and N and so let D be in D and N in the natural numbers. And of course, what we want to do is find this D prime. We need to find D over N, so to speak. And we're going to use the injective diagram to do this. So consider the following diagram. Where N is, of course, the same N that we have up here into Z. And this is the inclusion, right? So this is all multiples of N. This is Z. This is the inclusion map. Here's D. I'll call that F and H. Right. Let's see, I need to tell you what this map here is. Okay, so what I need to explain at this point is D is injective. Right. And we have well, so how should F work? Anybody want to tell me how F should probably work?
That is going to take N to T.
Okay, by the way, how do I know that this defines? I mean, because all I've done is say, okay, I've got to have this function from NZ into D, and what do? I just say F of N equals D. what a poor example I am setting for everybody here, right? Because all I did is tell you where one thing went. Is that enough? Well, remember, right, so in particular, what happens is F of NK, because remember, everything in here is the form NK, actually goes to KT. And it's pretty easy to see that this is an R module homomorphism, right? By the way, there's a slicker way to say that, you know, I mean, you could go through verify it's an R module homomorphism, but what kind of module, what kind of Z module is in Z? It's free. It's free, right? In this case, the basis is N, right? So NZ itself is free on N. And what have I done there? I've said, hey, N, go to D. That's good enough because it's free module, right? So let's see what this all gives. Because of the fact that this is injective, there exists H from Z into D such that when I do iota and then H, it's F. All right. And so let's let D prime equal. Anybody want to guess what D prime's got to be? D prime needs to be something over here. Anybody want to take a stab at it? How about this? Look where the generator of Z goes under H. You know what? I bet precious parts of my anatomy that this turns out to be right. Let's check it and cross your finger for me. So if you look at NB prime, right, which I hope is D, this is N H1, which is H of N, right? Which should be F of N because of the fact that this diagram commutes, right? N goes to H of N, they should be the same as F of N. And F of N is D. So N D prime is D. So D is. Everybody okay with it? Okay. Any questions? Yes, sir.
Is this one a generalized modules over other rates?
Yes, but not straightforwardly, right? In fact, what you need is you need something more general, like basically, if you like, I can show up. But what you need is you need instead of injective, you need like a home, right? Like so. It turns out one of the important things about this is on the homework, I gave you something that says you can use without proof for now that any module embeds into an injective module. It's a submodule of an injective module. And that module is a home module, right? Which is sort of why it's so big, right? But I can give you the details later if you like.
Okay.
Okay, so I'm going to give you these two theorems in tandem. One of them I'm not going to prove because it's part of your homework, and the other one's sort of a dual result. So here's kind of a projective and injective duality result. This theorem's kind of a beast. The following conjecture or the following conditions on the R module P are equivalent. Let P be an R module. The following are equivalent. One, P is projective. As per definition 661, our first definition, every short exact sequence splits. And 3. And this is so projective. Every short exact sequence that has P on the tail end actually splits. Right? It's important that it's P and it's important that it's on the tail end. And 3 is my favorite one. And this actually, in my opinion, gives the best picture of what it means to be projected. There exists a free module F, and our module K, such that F is isomorphic to direct sum K. So in other words, what it means to be projective is it is the direct summand of a free module. All right. By the way, let me point out that by symmetry, whatever this complement module K is also projective. Right, because it's also summand of a free module. Now let's look at 667, which is the dual result. Let I be an R module. The following are equivalent. Number 1, I is injective. 2, every short exact sequence. By the way, anybody want to guess what the form of the short exact sequence is now? Good. Good. Right. So now if I is at the head of the train, then it splits. And 3, I is a summand. Well, let me see. Or a direct summand of any module of which it's submodule. So another way to put this is, this one's not stated as cleanly, I don't think, but if there's a one-to-one map from I into some other submodule or into other modules, there's a one-to-one map from I into B, then that means B is I direct sum something else. Notice that these are kind of dual here, especially 2 versus 2 here. Right. Okay, so let us, before I prove this, let me give an example. Here is my first example, and I want to give a domain example later. Actually, when we later in this course we get dedicated domains, but here's the easy example that I can come up with of a projective module that's not free. Let R be Z6, right, as a ring over itself, and Z6 is free R-module. Right? I mean, just one element is what you need, right? It's free over one copy of Z6. And Z6 is isomorphic to Z2 direct sum Z3. It turns out that if you take these 2 submodules, that the 0 bar and the 3 bar, and the 0 bar, 2 bar, 4 bar, these are both submodules, even as the Z6 ring. So these 2 things by 666 number 3 are both projective, but it's impossible that they are free, right? Because they're too small. Z2 is not a direct sum of some number of copies of Z6 because this has got 2 elements in it. And any direct sum of Z6 either has 0 elements in it, which is certainly not the case, or a power of 6 elements in it, right? Or infinitely many, right? So these are both projective, not free. Everybody okay with me? Okay. So let us get to verifying this. Proof of 666. Of course, the other one is a homework exercise. Okay, P is projective, right? We want to show that every short exact sequence of that form splits. Okay. Well, whoops, I'm sorry, this should be a P. Now I want to use the projectivity. So watch this, nothing up my sleeve. Right, how about that? Now, what does this allow? Of course, this is exactly the diagram from injectivity right here, right? This is the identity map. So there exists H from P into B such that the diagram commutes. That is to say, when you do H and then G, this is the identity on P. So sequence splits. Everybody okay with it? Okay, that wasn't too bad. How about 2 implies 3? So now we've got every short exact sequence with P at the tail end splits. We want to show that this is the sum of the 3 modules, right? Everybody agree with it? Okay, I'm going to use a corollary. Every R module, projective or not, is the homomorphic image of free line. There you go. Free module. Let P be projective. Then there exists a free module. And such that this is on to. So that is to say, every module, whether it's projected or not, is a homomorphic in free module, right? Let me give you a short exact sequence. Do I agree with that? Now this sequence splits. Since the splits, F is isomorphic, P direct sum kernel. There you go. So the role of K is the kernel of P. Any questions? Finally, 3 implies 1. I'll probably have to finish this up next time, maybe. But this will kind of give you the idea here. What we have to do is, let's suppose that we have what we have to do is we now have to show, let me call this G, and we'll call this F. We have to show that there is an onto homo, or there is a homomorphism here, since the diagram. Everybody agree? And the tool that we have at hand is we know that P is the direct sum of a free module. Okay. I'm going to finish this very quickly with very few details. Think about this, and then I'll paint in the details. What do we know? We know that P is the direct sum of a free module, right? Agreed? And so notice that you have homomorphisms here, inclusion into P and projection on P. Right. And what did we prove about free modules? Any free module is projective, right? So this allows me to do this. Since this is free, it's projective. So there exists H prime such that when you do pi P, then you do F, this is H prime. Now, your burden is actually to get H here. All right. I would suggest to get from here to here, go inclusion into P and then H prime. See if that works, right? And we'll fill in the details next time. Okay, any questions on that? Any questions? All right, well, put that in your pipe and smoke it, see if you can figure it out. I'll make sure the details are filled in next time and we'll move on from there. Questions? All right, y'all have a good one and we will see you next time.